Hello everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll go through this section B topical MCQs for topic 8, which is on chemical equilibrium. So option A refers to 1, 2, and 3. Those are the statements that are relevant to whatever they're asking. B is 1 and 2, C is 2 and 3, and finally D is just 1, being relevant to whatever they're asking, okay? So in this question, we have a reversible reaction, but we catalyze these reversible reactions. So what is the effect of catalyst on a reversible system? So we know a catalyst increases the rate of both the forward and the backward reaction. And in doing so, you provide this alternative reaction pathway for reactions to happen, whether you're in the forward reaction or the backward reactions. So actually it will have a new lower activation energy for both the forward and the backward reaction, and therefore option 2 is correct. As I mentioned, you have an alternative reaction pathway that give you that new lower activation energy, and therefore more proportions of effective collisions can happen. So that is to do with an alternative reaction mechanism for the reaction. So that's to do with the alternative reaction pathway, alternative reaction mechanism in which the reaction occurs, all right? And the last one is on catalyst changing the composition of the equilibrium mixture. So that is saying that the catalyst affects equilibrium position and therefore equilibrium composition, all right? So that is not true, because all the catalyst will ever do is to affect the rate. It does not affect equilibrium, okay? So you need to be very careful of rate versus equilibrium. This is a very common kind of thematic questions that they like to ask in any kind of 16 to 18 years old chemistry curriculum, really. Have a look through the topical playlist on chemical equilibrium, and you will find rate versus equilibrium, and a lot of theory questions have been asked revolving around this rate versus equilibrium. Changing conditions and then changing catalyst, etc., yeah. So here the only 1 and 2 are correct, so that's option B. So in this question 7, we have two bulbs, R and S. They have this mercury manometer, which basically measures pressure, and they will be on the same level if the pressure here is equal to the pressure here, which initially that is the case because R contains the gas X, and gas X is at the same pressure as the nitrogen in S. So if you have same pressure here and here, this will be level. They won't be one higher than the other. They will be on the same level. They also told that the volume of R is twice the volume of S, but they are both at the same pressure initially. When I increase temperature, so temperature can affect equilibrium position, and these are the gases in bulb R, because you don't change the nitrogen in bulb S. You want to cause the mercury level in the right hand to rise. So you want the pressure there to be higher than there. So we want higher pressure on the left hand side than right hand side. Only when you get higher pressure on the left hand side, then this would push it down and this would be pushed upward. Only then your right hand limb of the manometer will rise up, okay? And when you start at the same pressure, because you start at the same pressure, how can the equilibrium changes to give you a higher pressure? I'll tell you one of them. If it is just nitrogen, you have no equilibrium. So it's just nitrogen. Even if you increase the temperature here, it's the same as increasing the temperature here, because you have a thermostat that controls changes in temperature. So nitrogen here, if you warm it up, if you increase temperature of the thermostat, by changing the thermostat, you increase the temperature. The nitrogen here and the nitrogen here will increase by the same temperature, and there will be no changes because it started at the same pressure, okay? Even if they expand under higher temperature, but you will still be at equilibrium. Well, when I say at equilibrium, I mean they will still have the same pressure, okay? So you have no equilibrium reaction, or dissociation or whatever. So therefore, still the same pressure on either side. So you won't have one having higher pressure than the other, okay? Especially when you start at the same pressure and both are heated up to the same temperature. I should have checked number 2 first. Number 2 is isomerization. How you can see that this is NC and this is CN. Alright, so the CH3 remain the same, but you have swapped the position. NC becomes CN. So they are different. They are basically isomerizing from one form to another. The enthalpy change, so you have an equilibrium now. The enthalpy change of the forward reaction is negative. So that means the forward reaction is exothermic. When you increase temperature, since the forward reaction is exothermic, the equilibrium will try and decrease the temperature. Your equilibrium will try to decrease the temperature by releasing less heat. By releasing less heat, your equilibrium will favor to the left. Okay, so temperature increase, equilibrium favors the left hand side. It favors backward reaction. But you started out with this equilibrium mixture. When you form one side more than the other, both are 1:1. So because both are 1 mole is to 1 mole, so they don't really affect the number of molecules inside here. Even when you form this side or you favor the forward reactions, it's still 1 mole giving you 1 mole, or going the other way, 1 mole giving you 1 mole. So because of the equal number of moles of gases on either side, right? So when you shift it to this side, you are not going to get a difference in pressure at all, because you have equal number of moles of gases on the left and on the right. Okay, so even temperature increase, favor backward reaction, no change in pressure. Okay, no change in pressure because you have same mole of gases on both sides of the equilibrium equation. 1 mole here and 1 mole there. So you wouldn't get higher pressure on one side than the other. So by right, if I check number 2 first, number 2 is impossible to give you this observation where the right hand of this mercury level goes up because of higher pressure here. So that means only one must be correct, and number 1 has different number of moles of gases. You have 2 moles of gas on the right, you have 1 mole of gas on the left. Forward reaction is endothermic. When I increase temperature, forward reaction try to absorb more heat to try and decrease temperature. When you absorb more heat, you favor forward reaction. So this will favor forward reaction as temperature increases. When you favor forward reaction, you favor the side with more gaseous molecules. When you favor the side with more gaseous molecules, you will increase pressure. You favor the side with forming more gaseous molecule, and therefore they will exert higher pressure. When you exert higher pressure on the left, they will push it down and this will push it up, and therefore you will see the right hand limb of the manometer rising up. In fact, when 2 is wrong, only 1 is correct. Okay? Looking at this question 8, you have phosphorus pentachloride. Well, they give you the equation. So chlorides of 3rd period element. So this could be asked in a theory question as part of a chloride of 3rd period element kind of chemistry. This is a redox because that chlorine has gone to 0. That chlorine is -1. That chlorine is still -1. So this species has been reduced and the chlorine has been oxidized. Okay, so this is a redox reaction. But this question is not about redox. This question is simply about equilibrium. So you introduce PCl5 through there. It has movable, tightly fitting plunger, so nothing is escaping. The gas inside is allowed to expand until equilibrium is reached. So this is important. Until equilibrium is reached. So now you're at equilibrium. When you're at equilibrium, that means this is not moving anymore because you're at equilibrium. You're allowed to expand until this stops moving. That is when equilibrium is reached. Okay? At equilibrium, some of PCl5 partially dissociate, so you get a bit of this, a bit of this, and a bit of this. Alright? But at equilibrium, there has been an equilibration of the pressure, so that the pressure inside is equal to the pressure outside, the plunger will stop moving once you reach equilibrium. So which statements are correct? Okay, so which statements are correct? If I look at statement number 2, if I push in the plunger, if I push this in, I will put more pressure on the gas because I would make the gaseous molecules closer together. Okay, so I will increase pressure, molecules closer together. But look at equilibrium, Le Chatelier. You have got 1 mole of gas on the left, you've got 2 moles of gas on the right. So 1 mole of gas on the left hand side versus 2 moles of gas on the right hand side. Right, so when you increase the pressure, the equilibrium tries to decrease the pressure by shifting to the side with lesser gaseous molecule. That is your 1 mole of gas on the left. So that means, therefore, your equilibrium shift or favor backward reaction. It will shift to the left. Okay, so when it shifts backward, you will have more PCl5. So that is correct because it shifts backward. So 2 is correct. If you go for number 1, the equilibrium pressure inside the syringe, because they say equilibrium, is greater than atmospheric pressure. This is atmospheric pressure exerting on there. That is your equilibrium pressure. The plunger will stop moving after you allow it to expand until you reach equilibrium. The plunger will stop moving. That means your equilibrium pressure equals to your atmospheric pressure once you reach equilibrium. So your equilibrium pressure will actually be equal, not greater, but equal to the atmospheric pressure, so that they are not moving anymore. Alright, so that's incorrect. So 2 is correct, 1 is incorrect. You're left with option C, which is 2 and 3. And then if we think about 3, the volume of the gas in the syringe, so the volume of gas in this syringe will be greater than if no dissociation had occurred. The volume of gas in the syringe will be greater than if no dissociation had occurred. I don't want to think too much into it. I mean, I've got the 2 being correct, I've got the 1 being incorrect. C must be the answer. Okay, so I can just move on. But let me think about this. I guess you can think about it. So if you just have 1 mole of PCl5, it's undissociated. There's just 1 mole of PCl5. But then when a bit of it dissociates, okay, 1 mole of these give you 2 moles of gases. So when you dissociate, you give you 1 mole of this give you 2 molecules of gases. 1 molecule give you 2 molecules of gases. So you will have more gases. You will fill up greater volume because you have more gases. They will occupy greater volume than if none of this dissociate. Alright, so number 3 is correct when you think about it that way as well. Okay, phew, okay. That was quite wordy, yeah? Moving on to this next question. So which equilibria, where all the species are gaseous, would have Kp with no units? So if you write for each of the equation, H2 plus I2 give you Hi, you need to balance the equation. So typically we will have gaseous iodine and hydrogen, gaseous iodine and gaseous hydrogen, but the iodine can easily sublime into gaseous iodine in the presence of heat. Alright, so if I use gaseous iodine for this reaction, so Kp will be partial pressure of Hi square over partial pressure of H2, partial pressure I2. Okay, if we assume the unit of partial pressure to be in Pascal, it could be in Newton per meter square, it could be in ATM. I'm just assuming it to be Pascal. So that will be Pascal square, that will be Pascal times Pascal. There will be no unit because Pascal times Pascal is Pascal square, so it will cancel out. Number 1, when you have SO2 plus O2, equilibrium, to give you SO3. So that's gas, gas, and gas. Don't forget to balance the equation. 2 of it, and 1 of it. So your Kp, it's PSO3 square over PSO2 square and PO2 to the power 1, because there's just 1 in front of O2 when you balance the equation. If I continue my assumption that the unit of pressure is Pascal, that will be Pascal square over Pascal square times Pascal. I will get 1 over Pascal, which you simplify to Pascal minus 1, because that and that cancel, get 1 over Pascal. So that one has a unit. That one has unit, which means 1 is incorrect, because you want an equilibrium constant with no unit. 2 is correct, 1 is incorrect. C must be the only answer. Okay, but let me just check. Number 3, CO plus steam, giving you CO2 plus hydrogen, CO2 and hydrogen. So the equation is balanced like that. And you can see everything is 1 to 1. And you can see Kp is just PCO2, PH2, PCO, PH2O. Everything to the power 1, because this equation is balanced by 1 in front of all the reactant. This will be Pascal times Pascal divided by Pascal times Pascal, no unit. As you have worked out, because number 2 was right, number 1 was incorrect, so 2 and 3 must be correct by logic. This is the last question of this 5-question section beta MCQ on chemical equilibrium. So we use catalyst in many reversible reactions. Okay, so we use V2O5, that is your vanadium 5 plus and O2 minus. Your LCM between 5 and 2 is 10, so you need 2 of these, you need 5 of these for the charges to balance, right? So this was the equation, the equilibrium that I showed you in the previous question. So what effect does this, which is a catalyst, so how does catalyst affect equilibrium? Catalyst does not increase the value of Kp, because only temperature can change equilibrium constant value. Nothing else, not concentration, not pressure. Okay, only temperature can change Kc or Kp or whatever equilibrium constant there is. Number 2 is definitely wrong. That means only 1 is correct. Another thing that a lot of students couldn't get is that catalyst speed up the forward reaction, but catalyst also speed up the rate of backward reaction. Okay, so catalyst speed up the rate of both forward and backward reaction. Yeah. And in terms of reverse reactions, it will also speed it up. So it's not increase, it's actually decreases as well. It's got a new lower activation energy for both the forward and the backward reaction. Okay, so I guess a simple diagram, it's probably the best way of representing it. If I have a reactant, if I have product, so I could have that, all right, but I could also have a catalyzed reaction like this. Now let me not do that. If I do this first, so this is energy, this is progress or extent of reaction, all right, or reaction coordinate. Let's say that is A, this is B going downward. So A is equal to, these are uncatalyzed, all right, uncatalyzed. A is equal to activation energy of forward, B is equal to the enthalpy change of forward. And then when you think about that is your activation energy of the backward reaction. So if I draw that as C, then C is equal to, let me not worry about enthalpy change first, let me just worry about activation energy. That will make our life a lot easier in terms of what I wish to explain here. Alright, so make that B. So B is activation energy of reverse and is for uncatalyzed. Alright, now if I have a catalyzed reaction, so let's say I have that, I still don't like that. So I will have the green one, which is C, and then I will have the catalyzed reaction. So the green one is catalyzed. C would be my activation energy of forward, but it's catalyzed. Alright, it's lower, you can see it's lower than uncatalyzed. But how about the backward reaction? Activation energy is from where you start to the top of the peak. Now actually I want to use a different color. Say if I use brown, from where you start to the top of the peak, because now this is reverse, but this is catalyzed reaction, reverse. So this is catalyzed reaction, and D is your activation energy of your reverse reaction, which is catalyzed. So as you could see, when you use a catalyst, alright, your activation energy of forward reaction is decreased, so your forward reaction gets faster. When you use a catalyst, your forward reaction, your reverse reaction also have lower activation energy. Okay, when you catalyze the reaction, your backward reaction, your reverse reaction also have lower activation energy than the uncatalyzed reverse reaction. So a simple diagram like this show you that catalysts affect the rate of forward and backward reaction. They do increase the rate of forward and backward reaction. Alright, so that's the end of this 5-question series tutorial on section B, kind of topical MCQ on chemical equilibrium. Click the button on the bottom right, subscribe to the channel to get more videos in the future and to support the work, and share the channel with friends, your various group chat, your wide network of contacts, and many more acquaintances that you think these videos or the channel can help other people you know. Alright, so thank you for sharing and thank you for watching. See you in the next video.